we're going to start chapter 2 tonight, and we have not covered section 1.7, and I am well aware of that. I am going to, as we go tonight, when we get to where we're going to need something from 1.7, I'm going to talk a little bit about what's in 1.7. We will certainly do enough for you to be able to do any problem that you're going to see on the final exam. As far as the 1.7 homework assignment, I'm just going to let you decide on that. In other words, we're not going to cover every single thing in 1.7. We're going to cover just what we need for what we're doing tonight and for what you're going to see on the final. If you want to do section 1.7, that's fine. If you do it and you complete it and make a 100 on it, or you make a grade on that homework assignment that would improve your overall course grade, I will count that grade. If you don't do it at all, I will omit that assignment. You know, if that assignment would hurt your grade, I'll omit it at the end of the semester. If you want to do it and you do, and you make 100 or you make a grade higher than your average in the class, you know, then I would count it. So that's kind of where we are. So we're going to look at 2.1 and 2.2 tonight, and again, a little bit of 1.7 as we get to where we need some stuff from there. So in chapter 2, just in chapter 2 in general, the topic is functions. And so what we're going to do tonight is you're going to be surprised to see that we're not going to do a ton of math per se tonight. We're going to get a ton of definitions and terminology and notation and just explain some ideas that relate to these things called functions. And we'll talk about exactly what a function is and so forth. But to introduce that idea, let's say we've got an equation like y equals 2x plus 1. So notice this is different from what we were doing in chapter 1. Now we have two different variables in that equation, right? Notice both variables only show up raised to the first power. So we would call this a linear equation, just like we did those equations in section 1.2. But the difference now is this is a two-variable linear equation. We're going to spend a lot of time with linear equations in section 2.3 and 2.4 next week. So here's the thing you've got to see about a two-variable equation. Now you've got to do more than just find a value to replace x with that makes the statement true to have a solution, right? Because whatever value you replace x with, you've also got to figure out what should I replace y with so that this statement is true. So I have written here, if x is equal to 3, then y is equal to 7. Do y'all see why that's true? If I replace x with 3 in this equation, y equals 2x plus 1. If I replace x with 3 here, do you see that when I evaluate that, when I calculate it, 2 times 3 is 6, 6 plus 1 is 7. When I replace x with 3, I literally get y equals 7. Do y'all see that? So what that's saying is, if I were to think of it this way, if I were to plug 7 in place of y, and I was to plug 3 in place of x, I would get a true statement. X is 3, y is 7. That statement is true. So notice, if I want to give that solution to this equation, I can't just say the solution is x equal 3. And I can't just say the solution is y equals 7. I have to say that the solution is x equal 3 and y equals 7. Y'all see that? So if I choose 3 for my x value, there's only one number I can choose for y that's going to make that equation true. And so this is how we write that. We've got parentheses, and inside those parentheses we have 3 comma 7. So that 3 comma 7 thing is called an ordered pair. An ordered pair. And we call it an ordered pair because the order matters. the first coordinate of that ordered pair, 3, in algebra, we always take that to be the x value, the x coordinate. And that second number, 7, the second coordinate, we usually call that the y coordinate, represents y. So you can see that if I said a solution was 7, 3, that would be incorrect, right? Because that would be claiming that if I plug 7 in for x and 3 in for y, I would get a true statement, which I won't. Because if I plug 7 in for x, 2 times 7 is 14, 14 plus 1 is 15. If I plug 7 in for x, then I would need to replace y with 15 for that ordered pair to represent a solution to this equation. Does everybody see this? And by the way, notice we've already got 2 different solutions to this linear equation. Remember those equations we did in section 1, 2, generally when we solved them, the solution would be just a number because, you know, the only variable is x, and that one number would be the one and only solution of that linear equation in one variable. Hopefully what you're seeing here is this equation is going to have lots and lots and lots of solutions, right? And each of those solutions will be an ordered pair. We'll look at a bunch of those solutions in a minute, but for now, let's just look at one of those other solutions, or a couple of them. So what I have made over here, this little chart, is a way that we can find some ordered pair solutions of this equation. So this says that when x is 3, y is 7, and that gives us the ordered pair 3, 7, and that's one solution to that equation. Do you agree that if I were to replace x with 0, I could find a y value that would also make that equation true? If I replace x with 0 here, what should y be? 1, I agree. Because y'all look, I'm not going to write it down. We should be able to sort of see how to plug that in. If I replace this x with 0, I've got 2 times 0, which is 0, plus 1, which is 1. So if I plug 0 in here for x, I'm literally going to get y equals 1. So there's another ordered pair solution, the one where x is 0 and y is 1. And if x is -2, if I plug -2 in for x, what am I going to get for y? -3, is that what you're saying? I believe that's correct. If I plug -2 in here for x, 2 times -2 is -4. -4 plus 1 is equal to -3. So if x is -2, then y is -3. And that gives me another ordered pair solution, -2, -3. Everybody see that? And hopefully what you're seeing from this is we found 3 here. We found 3 ordered pair solutions to this equation. Of course, we found another one a minute ago, 7, 15. That's an ordered pair solution. Hopefully what you're seeing is I could literally plug any number I want in place of x and find a y value to go with it that would give me an ordered pair that makes this equation true, right? Even weird values of x, like if I plugged, let's say we had y equals, let's say that I replace x with 0.1. Well, that would work. 2 times 0.1 is 0.2, and 0.2 plus 1 is 1.2. So if I replace x with 0.1 and I replace y with 1.2, that ordered pair is a solution of that equation. Does everybody see this? So the point is we can come up with as many ordered pair solutions as we want. We can't possibly write all of them down, right? Because do you see there are infinitely many ordered pair solutions to that equation? Because you could pick any number you want for x. Y'all look where I'm pointing, double that number, then add 1 to whatever you got there, and whatever that is, make that the y value that goes with it, and that ordered pair would be a solution. So So when we're studying functions, which this equation turns out to represent a function, we'll talk about all that in a few minutes. Mainly right now, I want to see that, make sure we understand what an ordered pair is and why they're important to what we're doing. Because with these two variable equations, every solution you're going to give is an ordered pair of numbers, an x coordinate and the y coordinate that goes with it. Because we can't actually write all those solutions down, oftentimes what we want to do is sketch the graph of this equation. And a graph is just a visual image of the solution set of this equation. And I know that sounds weird, but here's really all we're doing. So hopefully we're all familiar with this little construction here with the X and Y axis. So this is the X axis, that's the horizontal axis. The vertical axis is called the Y axis. Each of these are just number lines, right? And we don't typically draw the arrow on the left end or down at the bottom on the X and Y axes, but they're there. It's understood that they're there. So this x-axis is just a number line that goes forever in both directions. The y-axis is also a number line. It's just that it's been flipped up vertically. And so the way we label these is, this is x-axis is just a number line. So y'all look right there where the x and y axes cross, that's at 0 on the x number line. And so this would be 1, 2, 3, 4, 5, 6, 7, and so on, right? And to the left of the y-axis, you'd have -1, -2, -3, -4, -5, -6, and so on. And the same thing is happening on the y-axis. Where the y-axis crosses the x-axis, that's also 0 on the y-axis. And so as you go up the y-axis, you go to 1, 2, 3, 4, 5, 6, and so on. And below the x-axis, you go from 0 to -1, -2, -3, -4, -5, -6, and so on. So we've got these two number lines, and what that allows us to do is plot any particular ordered pair like 3, 7. We can plot that as a point in this space. So for instance, if I wanted to draw a visual image of the ordered pair 3, 7, here's what I would do. I would start here where the x and y axes cross. By the way, the point where the x and y axes cross, that is 0 on the x-axis. It's also 0 on the y-axis. So that point where the x and y axes cross, that is the point 0, 0. And we often call that point the origin. Origin like starting point, right? Okay, so if I wanted to plot this ordered pair where x is 3 and y is 7, I'm going to start at the origin, and I'm going to go 3 units to the right until I get to 3 on the x-axis. Then I'm going to go from there. Once I get out to 3 on the x-axis, I'm going to go straight up until I'm directly across from 7 on the y-axis. So I'm going to go from where 3 is here on the x-axis, I'm going to go up 7 units until I'm directly across from 7 on the y-axis. I'm going to put a point there, and that point represents the ordered pair where x is 3 and y is 7. Y'all see that? See, if I just wanted to plot a number, I would just use a number line, right? Like if I just wanted to plot the number 3, I would just draw a number line and put a dot on 3. But we've got to plot 2 different numbers sort of at the same time. So what we're actually doing is we're using 2 number lines, one for x and one for y. But what you can do is you start at 0, 0, you move till you get to where your x coordinate is, in this case 3. Then you move up or down however many units you need to until you get directly across from whatever that y coordinate is. and that's where you plot your point. Notice if you look straight down, you see the x coordinate 3. If you look straight to the left, you see the y coordinate 7. That's the ordered pair 3, 7. Everybody familiar with that idea? So we're plotting ordered pairs. This system that we're plotting in with the x and y axis, notice what it does is we've got a plane. A plane is a flat two-dimensional surface that goes forever in both directions. So think of this sheet of paper as a plane, except imagine it's a sheet of paper that's infinitely wide and infinitely long, right? And so what the x and y axes do is they break the plane up into 4 regions, right? This region above the x-axis to the right of the y-axis. By the way, we usually call that quadrant 1. So the x and y axes break the plane up into 4 quadrants. And so this quadrant is quadrant 1. Above the x-axis and to the left of the y-axis is quadrant 2. Below the x and to the left of the y is quadrant 3. And below the x and to the right of the y-axis is quadrant 4. And they're always labeled this way. You'll never see them labeled differently. The quadrants are always labeled with Roman numerals, and you always start with the upper right quadrant and you number them counterclockwise, 1, 2, 3, 4. Everybody see that? So that point is in quadrant 1 and we've plotted it. If we wanted to plot this ordered pair where x is 0 and y is 1, well, I'm going to start here where x and y are 0. The x coordinate there is 0, so I'm going to go 0 units left or right. In other words, I'm going to stay right there, but then I'm going to go up 1 unit until I get to 1 on the y-axis. And there we are. And so that point represents the ordered pair where x is 0 and y is 1. Everybody with me there? By the way, do you see that every single point on the y-axis is going to have 0 as its x coordinate? Because, for instance, here would be 0, 2, 0, 3, 0, 4, 0, 5, 0, -1, 0, -2, and so on. It's important to know that anytime you see an ordered pair whose x coordinate is 0, know that that's going to be a point on the y-axis. And you're just going to plot that point at whatever that y value is, in this case 1 on the y-axis. Okay, then we got this ordered pair where x is -2, y is -3. So we're going to go from the origin here to -2. So we're going to go 2 units to the left of the origin. 1, 2 to the left till we get to -2. Then we're going to go down 3 units until we're directly across from -3. So we go left to -2 and down until we get to -3, which is somewhere in there. Sorry, I drew that little line to 0, 0. And so that's how we plot ordered pairs. And every single ordered pair that's a solution of this equation, we could plot that ordered pair. For instance, do you agree that if I plug 1 in for x, I'm going to get 3 for y? Does everybody see that? If I plug 1 in for x, 2 times 1 is 2, 2 plus 1 is 3. So if x is 1, y is 3, well, I could come over here to 1 and up till I'm across from 3, and there's the point 1, 3. Everybody see how that goes? I could plot as many of those ordered pairs as I want. Here's the thing I want y'all to see. For this particular equation, if I were to connect all those points that I've just plotted, do you see that all those points are on a line? And here, when we say line, we mean straight line, right? All those points are on this single line. And it turns out that that line is what we'll call the graph of this equation, because what it turns out that every single ordered pair solution of this equation, y equal 2x plus 1, is represented by a point somewhere on this line. In other words, excuse me, if I were to just look at this point, Let me see if I can get it kind of close. There we go. There. So that is the point where x is 2 and y is 5, right? X is 2, y is 5. I'll bet you that if you plug 2 in for x and 5 in for y, you would have a solution to this equation, right? And you do, 2 comma 5. So every point on this line, if you figure out the ordered pair that that point represents, that ordered pair will be a solution to this equation. And conversely, every ordered pair solution to this equation is a point somewhere on this line. So we would call that line the graph of the solution set of the equation, right? I'll usually just say a graph of the equation, but we're actually talking about the equation's solution set. Everybody with me there? Mainly I did that just because I want y'all to see what an ordered pair is, because our definition of function depends on us knowing what an ordered pair is. So here are several definitions. Monday night students, y'all have an advantage here. Y'all have already got writer's cramp from this Monday night. I'm just going to give y'all a minute to write these down. I'm going to kind of talk through them, but then I'll leave that up for a minute where everybody can get this written, or you can take a photo of the screen or whatever you need to do. So there's these first two definitions are related to each other. So it says that a relation is any set of one or more ordered pairs. A relation is any set of one or more ordered pairs. So you could have a set with one ordered pair in it. That's a relation. You could have a set of 3 ordered pairs. That's a relation. You could have a set that includes 1,000,000 ordered pairs. It's a relation. Or a set that includes infinitely many ordered pairs. That's a relation. Any set of ordered pairs is a relation, whether there's one in the set or infinitely many or anything in between. A function is also a relation, but notice it's a real specific kind of relation. So a function is any relation in which no 2 ordered pairs share the same first coordinate. So it's a set of ordered pairs, but it's a set of ordered pairs where no 2 ordered pairs share the same first coordinate. We're going to look at some examples in a minute to make sure you've got this idea of what that actually means. The domain of a relation. It's just the set of all the first coordinates of ordered pairs. Or for us in college algebra, usually that we're going to say that's the set of all the x coordinates of those ordered pairs. And the range is just the set of all the second or y coordinates of the ordered pairs. So let me show y'all just a few little examples. I'm gonna leave those up there just a second. Y'all I'm just gonna kind of judge by when I see my Greenville students putting their pencils down. Anybody still writing that stuff out, or y'all just snap a picture or what? Okay, so here is a set of ordered pairs. There are 4 ordered pairs in that set, right? -3, 2, -1, 4, and so on. 4 ordered pairs in this set. First of all, we know it's a relation because it's a set of 1 or more ordered pairs. Is that relation a function? Based on our definition here, is this relation a function? Yes. I agree, it is, right? No 2 of these ordered pairs have the same first coordinate. They're all different. -3, -1, 1, and 3. As long as all the first coordinates are different, as long as you don't have 2 ordered pairs with the same first coordinate, it's a function, right? The domain of that function. The domain of that function is just the set of numbers -3, -1, 1, and 3. It's just the set of all the first coordinates. And the range is just the set of all the second coordinates. So the range is going to be the set of numbers 2, 4, 6, and 8. Everybody see that? Is this a function? So we know it's a relation. Is this set of ordered pairs a function? Yes. Do y'all say yes? Everybody say yes. I agree. Now notice you got a second coordinate that's getting repeated over and over again, right? But there's nothing about second coordinates in our definition of function. Doesn't matter if every ordered pair is the same second coordinate. As long as the first coordinates are never repeated, it's a function. And the domain of that function is just a set of numbers 1, 2, and 3. And the range of that function is literally just the set that only has the number 2, right? Like you don't have to write 2, 2, 2. It's either in the range or it's not, right? Okay, is this a function? Let me write another one real quick. Is this a function? No. So this one was. So it's a relation, right? Relation, but not a function. Everybody see that? Why? Because I've got one of the ordered pairs here gets repeated, right? The first coordinate gets repeated. We can still talk about its domain and range, right? Its domain is the set of numbers 1 and 2. And its range is the set of numbers 7, 9, and 11. And it's a relation, but it's not a function. Okay, how about this one? So that's a set with one ordered pair in it. Is it a function? Does everybody at least agree it's a relation? Because if we look back at our definition of relation, it says any set of one or more ordered pairs. And that is a set of one ordered pair. So it must be a relation. So then the question is it a function? It is a function. And this is an easy one to trip up on. It's an easy one to trip on because where students get lost in whether or not that thing, see if I can get them where you can kind of see the definition at the same time. Where students sometimes get lost in this is, it says a function is a relation in which no two ordered pairs share the same first coordinate. And sometimes students will see that two ordered pairs and they'll look at this and go, oh, well, that can't be a function because it doesn't have two ordered pairs. See, this doesn't say that it has to have at least two ordered pairs. It says it's any relation. Well, this is definitely a relation. Any relation in which no two ordered pairs share the same first coordinate. Well, you can't have two ordered pairs with the same first coordinate if you only have one ordered pair. Everybody agree? So that is actually a function. And you can sort of extrapolate from that any set of only one ordered pair is a function, right? Because you can't have two ordered pairs with the same first coordinate if you don't even have two ordered pairs. With that said, we don't care anything about these kinds of functions. Like I can't think of a single instance where we would be interested mathematically in a function that only includes one ordered pair. But just in terms of what the definition is saying, any set of only one ordered pair is a function. And by the way, the domain of that function is just the number 3 and the range is just the number 6. Everybody with me there? So, okay, that's what a function is. By the way, that's all a function is. A function is nothing more and nothing less than a set of one ordered pairs where no two ordered pairs share the same first coordinate. where students start getting a little bit confused sometimes with the idea of function is because we tell you a function is a set of ordered pairs in which no two ordered pairs share the same first coordinate. And then we'll have an equation. Yes, you blank paper here. We'll have an equation like this, which I think is the one we looked at a few minutes ago. And your math teacher will tell you that a function is nothing more or less than a set of ordered pairs where no two ordered pairs share the same first coordinate. Then they'll say, take a look at this function. And you might be thinking, well, this isn't a function. It's not a set of ordered pairs with different first coordinates. It's an equation. Technically, you're correct. This is not a function. But I'll call it stuff like this a function all the time. I'll say, let's take a look at this function. Technically, when I say take a look at this function, what I'm really referring to isn't the equation itself. It's the set of ordered pairs that makes up the solution set of this equation, right? So if we were to look back at where we found some ordered pairs to that equation a few minutes ago, you know, this equation y equals 2x plus 1, it defines a particular set of ordered pairs, right? And we know what some of the ordered pairs in that set are. 3, 7, 0, 1, -2, -3. I think we then found 1, 3, and 2, 5, and 7, 15. So the thing we run into is most of the functions we're interested in have infinitely many ordered pairs in that set. We can't literally write them all down. So what we can do, though, is we can write an equation. This is sort of a map to a particular function, the function that this is the solution set for. So in other words, I can't write all these ordered pairs down, but using this, I'm going to call it a rule, R-U-L-E rule for finding ordered pairs. It's like a map to the ordered pairs. I know that if I were to replace X with 5, for instance, I would need to replace Y with 11, right? Does everybody see that? Because 2 times 5 is 10 and 10 plus 1 is 11. Or if you say, okay, in this, whatever this function is that you're talking about, that you can't actually write all the ordered pairs down because there are infinitely many of them, in this function that you're talking about, which particular ordered pair has 10 as its x coordinate? I would tell you it's the one that's got, what, 21 as its y coordinate. Everybody see that? Because this tells me how to find the ordered pair that has 10 as its x coordinate. Plug 10 in place of x. 2 times 10 is 20. 20 plus 1 is 21. So when x is 10, y is 21. That's the ordered pair in this function that has 10 as its first coordinate. Everybody see that? So, okay. Equations then, we'll call them. A lot of times I'll say, look at this function. But technically what I'm referring to is the set of ordered pair solutions of that function. And then, as Emerald would say, just to kick it up a notch, sometimes instead of seeing this equation written like y equals 2x plus 1, you might see it written this way instead, and that's just f with an x in parentheses. And we would read that f of x, f of x. That's shorthand for f is a function of the variable x. Notice these two equations are the same equation. They represent the same function. They define the same set of ordered pairs. All I've done is I have replaced y with this f of x thing. And what I've written here, we usually, when we write an equation this way, instead of with y for our second variable, we're using what's usually called functional notation. And f of x literally means the same thing as y. And I know what some of you might be thinking. Well, if f of x means the same thing as y, why can't we just use y? Because that seems a lot simpler. And I don't necessarily disagree. And sometimes I will use y, but sometimes I will use f of x. It kind of depends. It depends on my mood, but it also kind of depends on the situation. Because let's say that we did want to find a few ordered pair solutions to this equation. If I'm using this y equals 2x plus 1 notation, then I'm going to have to literally say, okay, find y when x is equal to 3. Find y when x is equal to negative 2. You know, find y when x is equal to 5. Every time I want you to find one of those. But using functional notation, I could just write f of 3. Remember, this is read f of x. I could just say, I could write this out and then say f of 3. And what that should tell you is you're supposed to look over here on the right-hand side and replace the x there with 3. Do y'all see that? And this makes the most sense in the world if you think about it. Here's why. Remember what we've already established in chapter 1 is when you have an equation, whatever you do to one side of the equation, you have to do the exact same thing to the other side, right? So I did do something to this equation. So when I write f of 3, I changed something on the left side of that equation. There used to be an x in those parentheses, and I replaced that x with the number 3. Well, if I replace x on the left side with the number 3, then I have to replace x on the right side with the number 3. Y'all see? So when I just write f of 3, that's literally instructing me what I'm supposed to do. Plug 3 in place of x, and of course, evaluate it. And 2 times 3 is 6, plus 1 is 7. And so what we would say then, y'all look here, is that f of 3 equals 7. Now, what we already saw on that first little thing we did here, what we already saw is, or we've already seen that when x is 3, the y value that goes with it is 7, or that this equation has the solution 3 comma 7. So remember, in that ordered pair, the x coordinate is 3, the y coordinate is 7. Do you see what I mean when I say that f of x literally means the same thing as y? See, f of 3 is just the specific y value that goes with the x value 3. Do y'all see that? So when I see that f of 3 is equal to 7, well, I know that 3 is what I replaced x with, literally, right? So that's the x coordinate. F of 3 is simply the y coordinate that goes with that x coordinate. Do y'all see that? And so one thing this functional notation does really well is it makes it really easy for me to ask you to find functional values. I could just say find f of negative 2. When I say find f of negative 2, and I've got the equation written this way using the functional notation, you know what that's telling you to do. Replace this x with negative 2. And we're going to find negative 2. What was it? Negative 3, right? 2 times negative 2 is negative 4, plus 1 is negative 3. And of course, f of negative 2 is equal to negative 3. That tells me that when x is negative 2, the y coordinate that goes with it, because f of negative 2 simply means the y coordinate that goes with the x coordinate negative 2. So that y coordinate is negative 3. Everybody see that? Okay, we're going to do one more of these where we just plug something in place of x, but this one looks a little bit different. So find f of x plus h. That looks a little trickier, right? In fact, let's just look at that in a vacuum. Let's just say that I didn't show you what I did over here, and I just wrote f of x plus h. Remember that f of x is equal to 2x plus 1. This looks a little bit more daunting than just f of 3, but it means the same thing. So when so y'all look back up here, when in f of x, when I replaced that x with 3 on the left, that told me to replace the x with 3 on the right. Well, here I have replaced x with x plus h on the left. Well, that's telling me that I need to look on the right side of that equation, which is 2x plus 1. But if I replace the x on the left side with x plus h, then I have to replace x on the right side with x plus h as well, right? And so this thing is f of x plus h. And by the way, I should simplify that and say that that is 2x plus 2h plus 1. So that is f of x plus h. I don't know what h is. I don't know what x is either, unless you tell me what number to plug in for it. But it doesn't matter what it is. This would be the function f of x plus h. And we're going to come back to that toward the end of the night. The point I'm making here is it doesn't matter what they plug in place of this x here. Whatever they replace x with on the left side, they're telling you wherever there's an x on the right side, replace it with that exact same thing, right? Everybody see that? So, okay. So sometimes we'll use an equation to represent a function. Oh, and one other thing I should tell you about this functional notation. One reason functional notation is often used is because, for instance, if you take a business math class, you'll have one equation, like maybe that equation might represent the cost to produce X units of whatever you produce and sell. And this equation might represent how much revenue you bring in, how much money you make when you sell those X units, right? Of course, I'd be saying you're selling them for $40 a piece, right? Times the number of units you sell. This is telling you it costs $20 each to make them, times the number you sell, plus you may have some operating costs like electricity for your building, or maybe the lease payment on your building that you pay every month, the same amount whether you produce them or not. But that's neither here nor there. This might represent the cost of producing your product. This might represent how much money you bring in for selling your product. And this might represent that might represent the profit you make. So cost, revenue, and profit. So you wouldn't want to call those, you wouldn't want to write those three equations, y equals 20x plus 500, y equals 40x, and y equals 20x minus 500, because if you do, then when I say look at the profit equation, you're going to say, well, which one is that? Well, it's the one that says y equals, yeah, y equals what? It's this bottom one here. But see, this way, when I tell you to look at the cost equation, you know, C of X, that must be cost. Look at revenue, you know which one I'm talking about. Look at the profit equation. So sometimes we're working with more than one function within the same, you know, the framework of the same problem. And so we can give those functions different names. You know, when I write f of x equal 2x plus 1, I have given that function a name. That is the function f. It's like a little label. And you can see why we use f a lot, because it's just the generic, you know, first letter of the word function. But if I were working with two different functions, which we will be doing later in this chapter, if one of the functions is y equal 2x plus 1, and one of them is, say, y equals 3x plus 7, then I could do this. I can give them two different names, right? And so then if we're working with both of them within the same problem, it's real clear which one I'm talking about at any given point in time. I would just say, look at our function f, you know which one I'm talking about. Look at the function g, you know which one I'm talking about. So you can see that there are a couple of reasons why sometimes we use that functional notation. We need to be familiar with it, but you also need to realize it's interchangeable with the y notation, right? These aren't two different equations. It's just two different ways to write the same equation. Okay, So when we did look at that equation y equal 2x plus 1, we talked about the fact that you could sketch the graph of its solution set. Well, here's the thing. We're going to often want to graph the solution set of an equation. But we also want to be able to look at that graph and figure out whether that graph is a function or if it's a relation but not a function. And so the vertical line test gives us a real simple way, and I do mean it's simple. It gives us a real simple way to just look at a graph. Like, I haven't put any detail into this graph, right? I haven't labeled the X and Y axes with numbers or anything like that. I've just drawn very generic graphs here, but we can look at these graphs and instantly know which of these graphs represent a function and which of them represent relations that actually are not functions. So this first graph, does this graph represent a function? Yes. So in other words, all the points on this line, if you look at all those different ordered pairs, all the first coordinates of those ordered pairs will be different, and we can look at the graph and know that. How about the second one? Is this a function? Yes, no, or maybe?
Yes.
I'm going to say yes. We'll talk about why in a minute. How about this one? Does this represent a function? Yes?
No.
No? Okay, so that's a maybe. How about this one? No, everybody agrees no on this one. Okay. This one, this last one, is the only one that's not a function. So here's what the vertical line test says, and we're going to take a look at why it works. The vertical line test says that if there is any way that you can draw a single vertical line, remember a vertical line is one that goes straight up and down. If there's any way you can draw a single vertical line that strikes the graph at more than one point, then it is not a function. And so let's look at this one that I claim isn't a function. If I draw this vertical line, notice how it hits the graph at more than one point. Well, let's say if I did label these coordinates a little bit, maybe that's where X is -3 right there. Then do you agree that this ordered pair has -3 as its X coordinate? But that ordered pair also has -3 as its X coordinate. So do you see why, if there's any way to draw a vertical line that hits the graph at more than one point, it can't possibly be a function? Because at every point where that line hits the graph, it's going to have the same X coordinate, right? In fact, every single point on this vertical line I just drew has -3 for its X coordinate. Everybody see that? So not a function. On the other hand, these others, like here, I draw a vertical line, I only hit the graph once. Wherever I draw a vertical line, I only hit the graph once. Same is true here. I draw a vertical line, I only hit the graph once. Wherever you draw a vertical line, the y-axis is a vertical line, it only hits the graph once. This also passes the vertical line test. Now, somebody said, no, this isn't a function. I know why you're thinking that, because you're thinking about the fact that it kind of, like if I draw this horizontal line, it hits the graph in 1, 2, 3 different points, right? All that says is that those 3 points have the same y coordinate. Do y'all see that? Like maybe that's where y is 1 on the y-axis. Those would be 3 points that all have 1 for their y coordinate. But remember, it's okay if y coordinates get repeated. Same is true here, right? These 2 points have the same y coordinate, but that doesn't matter. They got different x coordinates. Everybody see that? So, okay, vertical line test. It's a super easy way to see if we're working with a function or just a relation that's not a function. Incidentally, in this course, virtually exclusively for the rest of the semester, everything we work with will be a function. In other words, any equations we work with in this course, the graph is going to pass the vertical line test, except in the very last section of chapter 2, we are going to briefly look at equations of circles. In other words, it's an algebra equation, but if you were to figure out all the ordered pairs that make that equation true, they'd be the ordered pairs on a circle, and obviously a circle does not represent a function, right? That's the only thing, I believe I'm correct in saying, that is the only thing we're going to look at in this course where we're looking at something that's a relation but not a function. The main reason we look at equations of circles is because for those of you who take pre-calculus, which is trigonometry, circles are super important. And so, you know, they want you to have seen what that equation like that looks like. Okay, so vertical line test. Here's where I'm going to have to jump back a little bit into section 1.7, which remember we skipped. And we're going to talk about it, then we're going to take our break, and then we'll come back and look at, basically that was 2.1. We're going to come back and look at what's 2.2, although there's a tiny drop of 2.1 in that also. Okay, so we want to talk about interval notation. This is from section 1.7. We did not cover it. It was not on the test. It won't be on the test, but there is one problem on the final exam, and that problem on the final exam looks very much like this problem. So y'all do want some notes here, even though I'm not requiring you to do the homework from that section. So if this is an inequality, right? And this is a little more complicated than a very simple inequality. We're going to look at one or two of those as well, but I just want to start off with one that's very similar to what you're going to see on the exam, on the final exam. What this says, if I read this, remember our inequality symbols. Less than, I'm not going to write them. You can if you want to. Less than or equal to, less than or equal to, greater than, and greater than or equal to. And so this says, asks us to solve 8 is less than or equal to 5x minus 2, which is less than or equal to 18. In other words, we want only the x, we want all the x values, but only those x values that make this expression equal to a number that's between 8 and 18, including 8 and 18, right? Because of the or equal to part. Solving this thing is super easy. It's much like solving those linear equations we did in 1.2. Think of it this way. What I want to do is get x by itself in the middle. And think of it this way. We know that when we have an equation, whatever you do to one side, you have to do to both sides. Well, think of this inequality, right? This is actually not an equation, it's an inequality. Instead of an equal sign, we're using inequality symbols. Think of it like this. Whatever you do to one side, you got to do to all three sides, because it's sort of like you got a left side 8, you got a right side 18, you kind of got a middle side too, 5x minus 2. So you got a left, middle, and right. And whatever you do to any one of those, you have to do to all three of them. So I know that my goal is to get x by itself in the middle. So do you agree that to start accomplishing that, I should add 2 in the middle? Everybody see that? But if I'm going to add 2 in the middle, I have to add 2 on the left, and I have to add 2 on the right. Everybody see that? So it's really that basic sort of golden rule of equations we've been working with. It's just extended because now this thing has more than 2 sides. You have to add 2 to every side, the left, right, and the middle. And so when I do, I've got 8 plus 2 is 10. That's less than or equal to 5x, which is less than or equal to 18 plus 2 is what, 20. Okay, so now what do I need to do? I need to divide the middle by 5 to get x by itself. Everybody see that? Then, of course, I also have to divide the left side by 5, and I have to divide the right side by 5. So 10 divided by 5 is 2. I get 2 is less than or equal to x, which is less than or equal to 20 divided by 5 is 4. And so what this is telling me then is any value of x that's between 2 and 4 is going to make this inequality true. And by the way, that's including 2 and 4, right? Because I think we'll see, so let me write that original inequality again since I've crossed through some stuff up there. I think you'll see that if I plug 2 in for x, I'm going to get exactly 8. And 8 is definitely less than or equal to 8. It's not less than, but it is equal to. And 8 is definitely less than or equal to 18, right? And if I plug 4 in, I think I'm going to get 18 in the middle. And 8 is definitely less than or equal to 18. It's less than 18. And 18 is less than or equal to 18. It's equal to, right? And every number between 2 and 4 also make it true, right? Like if I plug 3 in. If I plug 3 in for x, oops, sorry, didn't mean to do that. I'd get 5 times 3 is 15. 15 minus 2 is 13. So if I plug 3 in for x in the middle part there, I'm going to have 8 is less than or equal to 13. And 13 is less than or equal to 18. And that's true. Y'all see that? So my solution set, this is kind of a one variable version, a little bit of a one variable version of what we've been talking about. How many solutions does this inequality have? We know that 2 is a solution. We know that 3 is a solution. We know that 4 is a solution. By the way, do you agree if I plug in anything bigger than 4, I'm going to get a number here that's bigger than 18, so it wouldn't work. And if I plug a number in for x that's smaller than 2, I'm going to get something smaller than 8, and that wouldn't work. So we know that 2 is a solution. We know that 3 is a solution. We know that 4 is a solution. We know that, for instance, 1 and 5 are not solutions. How many solutions does this inequality have? 3. How about 2.1? Would that work? Would 2.1 make this true? Of course it would. 5 times 2.1 is 10.2. 10.2 minus 2 is 8.2. That number's between 8 and 18. Do y'all agree? How about 2.11? How about 2.01? How about 3.999? How about 3.91? How about, so y'all see what I'm saying? We've got infinitely many solutions, right? Now, in this case, each solution is just a number because this just has one variable, but there are infinitely many solutions. What I could do is this. I could draw a number line and, you know, somewhere back here, I'm just going to start at, say this is 5, 6, 7. I can't even do that. Say this is 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And of course, that goes back to 7, 6, 5, 4, 3, 2, 1, 0, -1, and so on. And that keeps going to 19, 20, 21, and so on. What I could do is I could sort of draw a picture of that. Oh, it was 2 and 4. I was looking at 8 and 18. I'm an idiot. Okay, I can do that one. I could draw a number line and say this is, say, -1, 0, 1, 2, 3, 4. And what I could do is I could shade this part of the number line between 2 and 4 to say all the real numbers between 2 and 4. Now, here's the thing. At the end, because if this had not been less than or equal to, but had only been less than, y'all look, that would look like this. Do you agree that if I had this, 2 and 4 wouldn't actually be solutions? Because 2 has to be less than x. In other words, 2.1 would work, but 2 wouldn't, because 2 is not, if I plug 2 in for x, 2 isn't less than 2, right? It doesn't have the or equal to part. So 2.1 would work, 3.9 would work, 3.99 would work, but 2 and 4 themselves won't work. In this case, they do, because we have the or equal to part. So there's two ways to do this. And this is what interval notation is. So we're going to do the number line graph for 2 is less than or equal to x, which is less than or equal to 4. And then we're going to do the number line graph. Let me write it up here. 1, 2, 3, 4. Then we're going to do the number line graph for 2 is less than x, which is less than 4. So 2 is less than or equal to x, which is less than or equal to 4. Here's what I'm going to do. Some of y'all have been taught to put colored circles or colored dots here over the 2 and 4. They teach it that way a lot in middle school and high school. What we're going to do instead is, if it's got that or equal to part where these numbers 2 and 4 are actually part of the solution set, we're going to use a square bracket around each one like that. If we don't have the or equal to part, where 2 and 4 themselves are not solutions, right? Just all the real numbers between 2 and 4, all the real numbers that are bigger than 2 but smaller than 4. In that case, y'all may have been taught to draw uncolored in circles over the 2 and the 4, but we're not going to do that. We're going to use rounded parents, like parentheses, rounded parents over the 2 and the 4. So if these numbers on the ends are included in our solution set, we use square brackets. If the numbers on the ends, in this case 2 and 4, are not included in the solution set, in other words, we don't have the or equal to part, it's just the numbers between them, but not those numbers themselves, we use rounded parents. That's because that's interval notation. So 2 is less than or equal to x, which is less than or equal to 4. Here's how you write it in interval notation. It's just 2 comma 4 with square brackets on the end. And what that says is all the real numbers between 2 and 4, and remember there's infinitely many of those, right? All the real numbers between 2 and 4, including 2 and including 4. That's the set of numbers we're talking about. Whereas, if I had this instead, where it's just all the real numbers between 2 and 4, there's still infinitely many of those as well, but in this case, 2 and 4 themselves are not to be included in the set. I would write it like this. 2 comma 4, but with rounded parents. Now, notice that looks just like the ordered pair 2, 4 that we've just been talking about, whose x coordinate is 2 and whose y coordinate is 4. Do y'all see that? So you've got to be careful and not get yourself confused. Math is often like language, and in language, context is important. So for instance, quick example, if I can find a clean sheet of paper somewhere. If I wrote this word, what is that word? Wound? Are we sure about that? Are we sure that word is wound? What else might it be? Of course it could be wound. So I agree that word is either wound or wound, but when you look at that word, there's really no way to know which word it is. Do y'all agree? But if I wrote this, now what word is that? We all read, right? What is that word? Wound. What's this word? Wound. The point I'm making is we have all kinds of things like this in the English language, right? By the way, English is one of the hardest languages, and they say the second hardest language in the world for non-native speakers to learn. I wouldn't know because I'm not a non-native speaker, but supposedly the only language that's harder to learn is Mandarin Chinese. This is one of the reasons why English is a hard language to learn. As I understand it, for example, Spanish, they don't run into this kind of stuff. So notice how here these two words are spelled exactly the same, pronounced totally differently and mean two totally different things. I am told that in Spanish, when you have a group of letters that makes a particular sound, it always makes that sound. Whereas in English, sometimes OU sounds like ow, and sometimes it sounds like ooh, right?
Yeah, my dad said it's really hard.
Say that again.
My dad said it's the hardest.
Is your dad, is his native language Spanish?
Yeah.
Yeah, and he finds English difficult. That's
Makes
because,
fun of it all the time.
yeah, it's very make funnable. English is a language that's easy to make fun of. We got more weird stuff. Like, for instance, we also have this problem. First of all, that could be read or it could be read. Do y'all agree? I might be gonna read a book, or I might be saying I read a book. But then again, if I just say the word red, I might be talking about the color. Do y'all see what I'm saying? Two words that are spelled totally differently, but pronounced exactly the same. So English is eaten up with that kind of stuff. The only point I'm making, I know we got to get to a break. The only point I'm making is you've got to be able to separate. You've got to be able to look at something like this and recognize, okay, in this context, this is how they've written this interval of numbers. This is interval notation. But if I'm looking at a graph of a line and I see a point on that line and beside it I see 2, 4, I've got to understand, oh, in that context, that's the ordered pair. That point is the ordered pair whose x coordinate is 2 and y coordinate is 4. Y'all see what I'm saying? And you're going to see, even tonight after break, you're going to see that sometimes we're using ordered pairs and interval notation within the same problem. So you do have to make sure that you can sort of separate which is which. Okay, real quickly, and then we're going to take a break. Let me just run through some real quick. I've written a bunch of little number line graphs, and I've shown you what each of these mean. And I'm going to run through them quickly. These couple at the bottom are the ones I really want to get to. These two we've sort of seen. This is saying all the real numbers between -2. I'm sorry?
Can you please zoom out just a little bit?
Can you zoom out?
Zoom out, okay. Well, we haven't got to the bottom yet. I probably need to zoom in. Can y'all see that okay? Okay. So does everybody see that this is the set of all real numbers between -2 and +2? So it'd be -1.999 ... all the way up to, oh, and 3. I don't know why I put 2 there. I did that on all of them. That's 3. That's 3. 0, 1, that is 2. Okay, so this is all the real numbers between -2 and +3. So -1.999 ... is in this set. 2.999 ... is in this set. Everything between -2 and 3 is in the set, but -2 is not in the set and 3 is not in the set. And interval notation, it would just be the interval from -2 to 3. By the way, when you got the parents on both ends, that's called an open interval. The ends of this interval are open because you can't literally write down the smallest number in the set. You know, -1.99, but there's another number smaller that's in the set, -1.999, and so on. And you could do that forever. Here we've got the same set, except here it's not only all the numbers between -2 and 3, but -2 and 3 themselves are also in that set. So of course I'm going to write it with the square brackets. We call that a closed interval because it's closed. 3 is in that set and nothing else gets in. In a closed interval, you can always tell me what the smallest and biggest number in the set is, right? -2 is in the set, nothing smaller is allowed to be in. 3 is in the set, nothing bigger is allowed to be in, and everything between those. Here, this interval goes from -2, oh no, it does go to 3. Dang it, why do I keep doing that? It goes from -2 to 3. Notice there's a square bracket on one end and a rounded parenth on the other end. Square bracket on one end, rounded parenth on the other end. First of all, that's called a half open interval. And half open interval. So if one end has a square bracket and the other end has a rounded parent, we always call it half open. We could call it half closed, but we don't. We always say half open. And what that means is this is the set of all real numbers between -2 and 3, including -2, but not including 3. Y'all see that? So -2 is literally in this set. 3 is not. 2.99 is, but 3 isn't. That's half open. Main thing I wanted us to look, and here is these bottom ones where, notice here I've colored the number line. I've shaded the number line from -2 all the way to the end, and I've shaded the arrow on this end as well. Y'all see that? So here's what you got to remember about a number line. The arrows on both ends, what that's telling us is this number line, if you keep going to the left, you're going in the direction of negative infinity. And of course, negative infinity is really just the idea that there is no smallest number, right? It keeps going forever. It goes to -1 million, it goes to -1 billion, it goes to -1 trillion, it keeps going forever, right? And infinity is the idea that there is no biggest number. It goes to 2, 3, 4, it goes to 100, a million, a billion, a trillion. It goes forever because there is no biggest or smallest number. So I have shaded everything from -2 all the way to the end of the number line, including the arrow. That is say this, that's how what the number line graph would look like if you graphed the set of all values of x that are greater than 2. And the way I would write that as an interval is the open interval from 2 to infinity. And so we never put a square bracket around positive or negative infinity, because if we did, we'd be saying we can somehow enclose infinity in a set, but we can't. Infinity is not like the world's biggest number. It's the idea that you can never enclose infinity because there's always a bigger number. Everybody see that? This is the number line graph for the set of all values of x that are less than 1. And we wouldn't write that 1, negative infinity. We would write it negative infinity, 1. Why? Because we always write the smaller thing on the left and the bigger thing on the right. And of course, it doesn't make sense to say negative infinity is smaller than 1. What it makes sense to say is all the numbers coming from the direction of negative infinity up to the number 1 are getting bigger as we go toward 1. Do y'all see that? And finally, if you want the set of all real numbers, like all the real numbers, the number line graph, you'd just shade the entire number line. And you'd put a rounded parent around negative infinity and a rounded parent around positive infinity. And it would just look like the open interval from negative infinity to positive infinity. By the way, I'm aware that when I say from negative infinity and to positive infinity, that's not accurate, because you can't come from negative infinity, because you'd have to get there first to come back from there. And you can't ever get to infinity, because if you could, it wouldn't be infinity. But y'all know what I'm saying. And that's just how we write the set of all real numbers if we're using interval notation, which is what we'll use. All right, we're going to take a break. It's later than normal, about 5 minutes later than I wanted it to be, but hey, it is what it is. I am going to stop the recording for the moment.